Okay. Yeah, hi also from my side, and actually thanks to Thomas and Elena for the setup, because your discussion plays perfectly in what I'm going to present today. And I know it's the last session before lunch, so I can promise you it will be the least methody presentation of this entire workshop. The method is super easy, and actually the reason why I'm presenting it is because it was born out of a necessity. So we're using mainly transition pathway models with a lot of years, so we have to aggregate something. And so that meant we had to do some time series aggregation, but we wanted to have short-term and long-term storage. And yesterday we had a long discussion about exact time series aggregation, really fancy time series aggregation, and Sonja said to make time series aggregation sexy again. Today I want to make time series aggregation unsexy again. So again, there's no machine learning, no classifiers, no nothing. And what we're discussing in this entire workshop are all the complexities that we have in our models. And the most established technique to reduce this is time series aggregation. First, because it contributes a lot to the number of variables and constraints that we have in our models, and also because we know that many hours in the year show very similar conditions. And I also know that here you can see two videos from my office window. They look very similar. It snows, and when it's snowing, I'm getting very excited and I take a video. But these two videos are 1.5 years apart. One was on April 18th, the other one on November 20th. That means, for sort of really stylized, we can assume that on April 18th and November 20th, solar radiance and heat demand were sort of similar. So these can be represented by the same representative hour. That's fantastic. However, if we compare this to a stylized natural gas storage, we can see these are definitely not the same hour. We cannot represent them with the same hour. So the issue here, as we all know, the storage level is time coupled. So the storage level depends on the previous time step. And if we formalize this, and this is the only equation you'll see today, is that the storage level in the current time step is the storage level in the previous time step, including a self-discharge term, and let's call it a net charging term. We can add more terms here, like spillage and so on, but like for now, let's just have a delta H of our net charging. And the problem is time series aggregation loses the chronology of these time steps, so this idea of a previous time step doesn't exist anymore. So the storage representation methods, as we discussed before, they must rebuild the storage level chronology. And what I would like to discuss today is first comparing these ideas of representative days and representative hours, as we sort of heard before, then highlight the limitations of current representative hour storage representation methods. I want to present the approach that we implemented, that we came up with for, again, large-scale multi-storage energy systems where we need to aggregate a lot. And then want to benchmark this against other methods, because you won't just trust me that it's the best model ever or the best method ever. I want to compare that to existing models. And actually something that was sort of spoilered before is probably the most established and most common way to solve this storage representation method. It's by Kotsu et al., the superposition method. So we keep a daily chronology. That's fantastic because we just have 24 consecutive hours. So over a day, we keep the chronology. So we have representative days. And then if we have longer term storage, we just superpose these daily storage levels with a storage level of representative days. And then we can also model longer term storage. The problem, though, is that representative days require a lot of representative time steps to approximate the input data, because we enforce that we have 24 consecutive hours. That means I can only include any type of seasonality with 48 representative time steps, so 2 representative days. Otherwise, I only have daily behavior. So here, using representative hours is fantastic because this requires fewer time steps for the same approximation quality. However, then the question is, why are storage representation methods based on representative hours underrepresented? And for me, until now, the storage level can't really be constructed super efficiently or accurately. And I want to briefly mention the three, I would say, most established methods for representative hours and highlight some of the limitations. And actually, two of the authors of these papers are in the room. Now, Sonja is actually not in the room right now, so don't get angry at me. So there are the three models. The first one is to fully resolve the storage level. There, Matteo is a co-author. I don't know if he remembers that paper. Then the state-space transition method of Sonja and chronological representative hours, as we heard before. And the idea of the fully resolved storage level is we just model every hour of the storage. That's fantastic. We can model short-term and long-term storage. However, this introduces a lot of additional variables and constraints and can become computationally challenging. Then the idea of the state space transitions is that we implicitly track the storage level transitions with central differences between the two states. However, this approximates and smoothens the storage level, so it doesn't track the storage level exactly. And what we heard before with the chronological representative hours, there the storage level time steps are the operational time steps, so they're always chronological. However, this strongly smoothens daily variability because you assume very long hours of the same representative hour. So what our idea is to get inspired by the first method, to actually track the storage level, but kick out all the storage variables that we don't need. And I want to briefly introduce this. So let's take a generic time series with 20 time steps. We aggregate this, or we cluster that somehow, it doesn't matter, to representative hours. And here we have 8 representative time steps. They're the blue bars here in the plot. And now the first method that I mentioned would then rebuild the storage level fully resolved, so we would have 20 storage level time steps. But the question is, can we reduce the number of storage level time steps? And yes, we can actually do that. And that is also an observation that Sonja had in her paper in 2016, because the storage behavior, does this work? Not really. The storage level behavior doesn't change over the same representative hour. However, as we've seen before in the beginning with the natural gas storage, we have the same, so here we have representative hour 2, and here we have representative hour 2, but the storage level between the two doesn't have to be the same. So we can say for every cluster of adjacent hours represented by the same representative hour, we need 1 storage time step. So every time we change the representative time step, we just add 1 storage level. And by doing that, we can save a lot of variables and constraints. Here in this fictional toy example, we reduce it from 20 to 13 storage level time steps. And what is cool about this, we don't lose any information compared to the full storage resolution, because we don't approximate anything here, we just group and kick out redundant time steps. So I want to quickly formalize this mathematically with the equation that we've seen before. Here I want to introduce 2 indices. Don't get scared by them. We have I and J. I are the representative time steps, representative hours here in blue, and storage level time steps in J are the green ones here. So for this interval, we have a constant net charging. So our delta H is exactly the same. So if we write our storage equation for every time step, we always add the same delta H. So if we then, we can then sum all of this up, and at time step 10, which is here, it's the end of our representative, or of our storage level time step, and time step 7 is here, it is before the time step. So the generic storage level constraint looks very, very similar to the one that we saw in the beginning. What gets a bit ugly is our self-discharge term, but basically what we do, we say the storage level at the end of our storage level time step is the same as the one before, plus our net charging, and this is basically just the duration of our storage level time step. And now I want to compare this with the existing methods that don't approximate the storage level. So we want to benchmark the proposed method here with 4 methods. The first one is the superposition method with the representative days that I mentioned before. Then there's a version of that where you have fewer constraints, which we call min-max, the full storage resolution, and chronological representative hours, here abbreviated as chrono. And we use a greenfield cost minimization model of the European electricity and heating system here for 28 countries, and we have 4 storage technologies: natural gas storage, hydrogen storage, pumped hydro, and batteries. And this is all implemented in our optimization framework, Zen Garden, and we use hierarchical clustering and mean representation, but again, the focus here is not on the clustering, but on the storage representation. So first, we want to compare the trade-off between accuracy and solving time. So here on the x-axis, you see the relative objective error, and we want to go to the left to the lowest objective error, and we want to go down in solving time. This is in a logarithmic scale to reduce solving time. And if we first compare the proposed method in green and the full storage resolution method in blue, we can see that the proposed method shows significantly lower solver times at, and that is important, the exactly same objective error because we don't introduce any approximation here. And at the strongest aggregation, we see a 20-fold increase in solving time for the full storage resolution. What I find quite cool is we don't have guarantees for error bounds. I'm sorry, but like in this model, even the strongest aggregation only introduces an error of 10%. So reducing 8,760 hours to 24 only introduces 10% relative objective error. If we now add this the chronological clustering, we can see that the accuracy and solving time is very similar to the proposed method, but at the strongest aggregation, the objective error is increased because we have really the smoothing of our objective value, of our daily profiles. And now adding the 2 representative day methods, we see that they're further to the northeast, to the upper right. So here we see that they have higher solving time and the highest objective error. Min-max can reduce the solving time because we can kick out a lot of constraints. However, in comparison to chrono and the proposed method, it's still further to the right and up. But of course, the objective error doesn't mean that the design is similar. So a low objective error doesn't mean that we have exactly the same design. So here I want to look briefly at the capacity error here for wind, solar PV, and fossil thermal. We also have some smaller technologies that I want to skip here. And we can see that the proposed method overestimates onshore wind a bit and underestimates solar PV. And the maximum error is for 48 representative hours, and it's roughly 40% lower. If we now add chrono, we actually see the intuitive behavior of chrono, that daily profiles are removed entirely for strong aggregation. So that means solar PV is more viable because we don't have any variability. And so the capacity is overestimated. And only when we have 2 representative hours per day, so 760 something representative hours, we see quite a good approximation of solar PV. And for the superposition, the representative day method, here we see quite a persistent capacity error, and the observation is flipped compared to chrono, that we have only daily profiles in the beginning, so a lower viability of solar PV. And now we've been talking about storage a lot, so I also want to look at how's the storage behavior captured. Here I look at the number of annual cycles, and we can see in the fully resolved resolution, we see that the hydrogen storage works as a long-term storage, and battery is a short-term storage, roughly daily behavior. So that's good. The fully resolved model works. That's nice. And we see that the proposed method shows quite a good approximation of the storage behavior, even at quite strong aggregation. The chronological clustering shows lower hydrogen storage and almost no battery storage until 768 representative hours because we kick out all daily variability. And superposition underestimates the use of hydrogen storage and overestimates the use of batteries. So with this, I would like to come to my conclusions. What we tried to do, again, it was really purpose-driven that we needed something to strongly reduce our computational load and to aggregate our time steps. And we wanted to keep the clustering accuracy of representative hours, but have a storage level representation method that we can use for computational tractability. And what we saw is that representative hours can cluster the input data or represent the input data time series more accurately. And what the storage level representation method shows a strong reduction in solving time while retaining quite a good accuracy, and it can represent short and long-term storage quite well. And for our purposes, and this is really transition pathway models, we saw that 100 to 500 representative hours are a good trade-off between accuracy in capturing our temporal behavior and reducing computational complexity. And with this, I would like to thank you for your attention, and I welcome any discussion of this. Thank you.